progress.
All right, as we are so kindly notified, recording is in progress, and we'll go on to actually start lecture a bit, because we actually had a question, and the question was about eigenfunction problems. And so eigenfunction problems sort of always have the same sort of format to them. They ask a question, they give you a system, some kind of H. So it's usually a linear time invariant system, has to be for it to work, because the eigenfunction property is only for linear time invariant systems. So they usually come in the form of an impulse response. What is an impulse response? It's specified as h of n, or if it's the DTFT of the impulse response, it will be capital H of e to the j omega. So those are the two possible representations for an impulse response. It's either in the sample domain, h of n, or in the frequency domain, h of e to the j omega. So you'll be given one of those two. And what you need to do is you need to apply the eigenfunction property. Now, the eigenfunction property says if you input an exponential or a linear combination of an exponential, which is a sinusoid, that same function will come out, but it will be multiplied by a complex constant, right? And so that complex constant that it's multiplied by is the value of the DTFT at the frequency of the input. Okay, and that is the eigenfunction property. So basically you take the DTFT function, whatever h e to the j omega is, and you plug in the value of the input, omega naught, right? And so that's what you do from a technical perspective to solve those. So that's all words, Dr. Willis. I'll write something down in just a minute, but that'll give you a better, like a tactile and visual feedback, but that's conceptually. That is, there's always a slide, technique for a solution. That is what the technique for a solution slide will tell you. Then we'll actually do it. Yeah. Oh yeah, there is. Thank you for pointing that out. Oh yeah. Yeah, this right here should some of that. Okay. Yeah, please remind me if I don't notice that there's a lot of technical components to executing all of this stuff well, and I need your help to make sure that I do that as best as possible. We are in lecture 7, okay, and so seems to be 2 copies of lecture 7, so I'll just guess that this is the one that we want. Yeah, it seems like the one we want, so I'll open this up. Okay. So eigenfunctions was actually we talked about eigenfunctions at the end of lecture 6. And so I want to, so here we are. Do I have some space? Here's some space on the side. I want to tell you, kind of give some annotations here about this eigenfunction property that we're discussing. So if you have an eigenfunction question, so eigenfunction question. All right, how do these present? Well, you'll be given an input. You'll be given something like x of n, and it will be either, maybe it'll just be a complex exponential, e to the j omega naught n, or maybe it'll be a constant times that, like a e to the j omega naught n. Or maybe it'll be a linear combination of it. Maybe it'll be a cosine of omega naught n plus phi. I think that was actually something extremely close to the homework. I don't know. So it's like, it's going to have one of these kinds of forms, complex exponentials going into the system. It's the input. All right. So the second part of that is that you're going to be given a linear time invariant system. It'll be either as an h of n, maybe it's an h of n is something like alpha to the n, u of n, or something like that. Just some kind of an impulse response that says it's a linear time invariant system. And this is what the actual system is. Or you'll be given the Fourier, the discrete time Fourier transform of that, which will be h e to the j omega. And in this particular case, if it were alpha to the n u of n, it would be 1 over 1 minus, anyone want to tell me what the Fourier transform of this is? Assuming magnitude of alpha is less than 1. Very good, yeah. So that's exact. So this, or you would get it in this form. Like these two forms are exactly the same thing, just in different. One's a frequency representation, the DTFT, and the other one is the sample domain representation. And so we know that when we put an eigenfunction into the system, what comes out is the same function multiplied by a complex constant. That complex constant is HE to the J omega, evaluated at omega is equal to omega naught. So really all you have to do is plug in omega naught here. All right, so remember, I'm gonna write again that this thing is a complex number, Z. Right, the only thing that makes this complex number like not able to write it down as a constant is that we do not know the value of alpha, we do not know the value of omega. Right, so if I tell you that alpha is equal to say 1/2, and I tell you that omega naught is equal to 2, this is a number. Right? It's just a complex number. And so that's what you would do. Like you would say 1/1 minus 1/2 e to the minus 2 omega. And that's a complex number. And so then that complex number would then multiply the that would be the A for this. In the case where you have the sum of two complex exponentials, which is a cosine, the magnitude of that number goes here, and the phase actually adds in to the phase of the complex to the sinusoid. So that answers all forms of all eigenfunction questions, sort of in terms of how you proceed and what you do. That'll help, and that's relevant to part of the homework. But hopefully that'll kind of okay. So we left off on symmetry properties of the DTFT. So we talked about a lot about how to calculate the phase spectrum and the magnitude spectrum of a discrete time Fourier transform, and realize that the key skills to do there is to always remember that life doesn't need to be complicated if we just look at these things and remember it's just a complex number. What is its magnitude? How do we get it? What is its phase? How do we get that? We can navigate these analytical problems. And we have a method for calculating magnitude, sort of looking at the magnitude of the numerator, looking at the magnitude of the denominator, and then taking, there's a process there. So I'm not going to go over it again because, well, you've seen it several times now. And I have this other way of calculating the phase response, which basically asks you to break the expression into real and imaginary components. And then you put all of the imaginary components in the numerator and all the real components in the denominator. You take the arctangent of that, and that's how you get the phase response. So just a reminder on that. These are techniques for a solution. So again, this is computing the phase spectrum techniques for a solution. You get asked to calculate a phase spectrum for something. This is what I recommend you do. Okay, symmetry properties. So lots of symmetry properties for the DTFT. All of these symmetry properties have their analog with the continuous Fourier transform. So if you were to look at the continuous Fourier transform symmetry properties, they'd look very much the same, except there wouldn't be n's. There would be parentheses around a t here instead of brackets around an n. And instead of e to the minus j omega, you'd have j omega like that. And so so all of these symmetry properties are in fact very, very similar, just a moment, to the symmetry properties of the continuous Fourier transform. Yeah.
On rows 1, 2, a little symbol between the x and the n, is that like conjugate symbol?
Yeah, this symbol here is conjugation. And so what this is saying is a conjugation in the sample domain implies conjugation in the Fourier domain. Conjugation and time reversal in the sample domain is double conjugation. Basically conjugate the conjugate. So it's like so what does that mean? Basically time reversal is also conjugation. let's see, if you have something that is real valued, if you have a real valued X, it leads to a conjugate symmetric DTFT. If you have a purely imaginary X, then that means that the DTFT is conjugate antisymmetric. If you have a purely even function, then what you get, so if you have the even part of a conjugate symmetric function, the Fourier transform of that is purely real. So what does that mean? I think what is that? So if I were to convert that to English, what is that saying? The way that that mostly means, like in most cases, if you have a real and even function, then you have a real valued Fourier transform. There's no complex values there. In fact, that's the whole, you guys know JPEG, like JPEG compression of images? It's the whole point of JPEG compression. JPEG compression, if you have a picture, say a picture of me, my smiling face, here I am, super happy. They take that picture, which is this upper left quadrant, and sort of mathematically speaking, what they do is they double it. And so say I had only one ear, then they would reflect it so that ear was like that. And so that would be the horizontal reflection to make it even. So this would be even about this point, right? So you take it and sort of flip it that way. And then they take it and they flip it vertically. So now my ear is upside down and I've got a frowny face, but that works with the upside down smile. And now over here, they flip that again. So I guess that would be something on the order of, what does that look like?
At the bottom right corner,
I guess it's something like this. Whoops, the ear's on the wrong side. So anyways, these are all symmetry properties. So I'm trying to show you how this symmetry is being satisfied in both X and in Y dimensions. So it has to flip across X, flip across Y, then flip across Y and X to get this last, this is flipped twice, so to speak. And so that is the basis by which they do JPEG compression. It's so-called the cosine transform. But the cosine transform is you can get it from a regular image by just reflecting the image and making it symmetric in both X and Y, and then take the Fourier transform. What you end up with is purely real values because this is even in this direction because we've done this reflection here across the middle, and it's even if you go in this direction, up and down. So left and right and up and down, it's even in all directions. So if you take the two-dimensional Fourier transform of this, you get a two-dimensional collection of real values. And that two-dimensional collection of real values, they take those values, they they quantize them, and they throw some of them out, and that's image compression. That's what's inside of a JPEG file. Fourier transform coefficients. Pretty cool, right?
and the values will be the density or
the actual values that they preserve are actually the Fourier coefficients.
the Fourier coefficient.
Yeah. If you go and you look up the JPEG transfer, so I actually did this for a while. JPEG compression, and you just click on the top link, and then you look for cosine, the discrete cosine transform, which is what I'm telling you about. And see these numbers here? Those numbers are Fourier coefficients.
And those would be the eigenvalues of the transformation.
Those are what they would call. You might call them, you might, so that they're often called basis functions. Like when you're trying to approximate some function in terms of a sum of other functions, they're called basis functions. And the Fourier transform can be seen as a trigonometric basis. It's a collection of basis functions that are all trigonometric in form. And so this would be yeah, exactly. It satisfies all of those properties of being both orthonormal and yes. So, but that's a little bit far afield from the content of this, but yes, they obey all of the Gram-Schmidt orthogonalization properties and all of that stuff related to interpolation. However, that is not the focus of our lecture, but it is an interesting thing when it comes to symmetry properties that we're discussing. Yeah. Yeah, in fact, there for a color image, there's actually our first project. We'll talk about this. So it's actually 3 channels. a red channel, a green channel, and a blue channel. And each one of those channels is a collection of values. It tells you sort of how intense red appears in the image. So if you have a purely red image, all of the pixels in the red channel would be max value. Usually it's a byte, an unsigned byte, so that would be 255. And all of the green channel and the blue channel would have only 0 values, and that will give you a purely red image. Now, if you want a purely green image, just the green channel is 255 and the other are 0. And a purely blue image, the blue channel is 255 and the other 2 channels are 0. So in fact, you're actually dealing with 3 images, 1 for each channel. And the superposition, again, this is linear. Color is linear. You add together red, you add together green, you add together blue, and what do you get? The color gamut. You get the color gamut of all possible visible light colors so that you can represent. And so if they're all 8-bit numbers, you get a 24-bit representation of color. And a 24-bit, how many values can you represent with 24 bits? 2 to the 24. And that's why, and so that comes out to something like some number of millions. And so if you ever hear about a monitor that displays so many million colors, where does that come from? 2 to the 24. It comes from that exact, there's no magic here, right? It just all makes sense, which is so wonderful about discrete signals. Yes, you had a question in the back. Yeah, okay. There's a lot to, all right, so there's a lot to cover here. So I work in imaging. So there's a lot of color space representation, since in fact, not all color spaces were created equal. We always use RGB. There's also YUV, like TV, broadcast TVs, and YCRCV. So this is like intensity, chroma, and luminance. And so even color can be represented in lots of different ways. And even the Fourier transform, which has one definition that we use in class, which is the forward transform. So when we look at our lecture slides and we look at the Fourier transform, in one direction we're multiplying by nothing, or the number 1, if this can catch up with me. So this is the Fourier forward transform, and the inverse transform, it has a 1/2 pi. And so in many, if I just type in Fourier transform and click here, well, you'll find some, so this is not always the case. So here we see there's 1/square root of 2 pi. And they have 1/square root of 2 pi in both the forward transform and in the inverse transform. So you can put this normalization constant in different ways. So I don't know if that answers your question about the square root of 2, but there's also different color spaces. And so here's a space color, and here's RGB. See the CMYK? Does anyone have a printer and had to put in different cartridges? What are the colors that you have to put in? Cyan, magenta, yellow, and K is black. It's a 4-component color space. What do you think CMYK is? Cyan, magenta, yellow, black. And why is that? That's actually the complementary color space. It's a color space where you're not. So in RGB, you're creating color through addition. In CMYK, you're basically creating color through subtraction. It's complementary color space. So that's why they have to have black. They have nothing to represent the absence of color, right? Because you can't subtract like that's. Anyways, it's sort of interesting. And if you ever saw this, anyone ever go on this viral thing about the dress that looked gold and the dress that looks like white to some people?
Many of fights when I was in school.
Oh,
really
okay.
did.
So you guys know about this thing. That's a great exercise in human perception and the ability for us to see color and how our brains interpret color. And it's actually relevant to color spaces. If you actually get into some science there and you talk about the science of perception and how the brain interprets color, you can get into some really cool conversations. And maybe you take that to the folks, back to those folks that you were having a chat with, and talk about complementary color. Some people see color in the sense of adding together things, and some people actually see it in the reverse. And maybe that will lead to different interpretations of the same image. All cool stuff. Totally unrelated to what we have. We have a midterm a week from now. Yeah.
This question, I'm not really sure. You had a JPEG is velocity compression algorithm.
That's correct.
Is that because the discrete version of the Fourier transform is more optimal?
Actually, that's an excellent question. And it's, so there is a lossless form of JPEG, like JBig, and that's because I actually worked in image compression for some time for analog devices. I built some chips and stuff. They're still around in devices, but yeah. So the whole idea of compression is to basically is this idea of energy compaction. So we talk about a signal and its energy, right? And we characterize signals by their energy. So, you know, like, is it absolutely integrable? Well, is it, if it's not, you can compute its Fourier transform. All right, the Fourier transform has this wonderful property that for most real world signals, when you calculate it, the Fourier transform of that signal, most of the energy is in the low frequency content. That means that the signals that we have in the real world tend to are mostly comprised of low frequencies. And there's actually only the high frequencies only contribute to very rapid changes. So our eyes aren't very sensitive to the high frequencies. Like if we throw out high frequencies, we may not see any difference at all. And so the idea of all compression theory is to change the representation of the data into another representation where there's less, where I can throw things out without you noticing. Okay. And you throw away the high frequencies. That's exactly, in fact, you can get an image that is extremely close to the exact image by throwing out nearly 90 to 95% of the Fourier coefficients. And that is the fundamental premise by which all compression theory works, whether it be AAC compression on audio, MPEG compression, video, image compression, JPEG, NG, whatever it is, you know, flat compression, all that stuff. So I don't know. Compression is a really cool topic. Maybe we'll do that for our project. But yeah, it's totally, it's easy to do, and it's surprising, but it's a little bit magic because, you know, it's hard to do if you don't know the theory. Like it just, how did all this happen? I don't know. How did you take this image with all this data? Raw, it would be stored, it would be many megabytes, but compressed, you compressed it into like 1 megabyte. How does this is magic? It's not. It's just some very well thought out mathematics. Yeah.
So do you do that with bandpass filters?
For sure, bandpass filters. You know, if the frequencies you care about, so signal processing is always a matter of getting what you want out of the signal, right? And if the stuff that you want, I mean, maybe you're a big fan of mid-range, you know, so you can do a bandpass filter and you make mid-range high and everything else zero, then that you get what you want. So it's all a matter of, so signal processing is a matter of identifying what you want in your source signal and finding a way to remove everything you don't want. And so even there can be structure there, like for images in medical imaging, where you're trying to detect tumors. There's a lot of structure there that matters to other people, but you're trying to detect a tumor. So the only thing that you want to pass through your filter are the pixels that are associated with cells that are cancerous or forming a tumor. So it's all sort of like how you form the problem and how you phrase it, and then you attempt to solve it. Okay, so symmetry properties, well, we got a little bit carried away with 5. So we're just going to go through the other ones a little bit quickly. So these are all symmetry properties based on real values of x of n. And they're just saying that, you know, if you have a real value, there's certainly things you can expect about its Fourier transform. Real part is even, imaginary part is odd, magnitude is even, and the phase is odd. That's what they all say here. That's what this stuff says. And all of that follows, all of these things follow from this. If you have something that's conjugate symmetric, then all that other stuff has to also be true. Yeah. If it's conjugate, it's going to have the same magnitude on the left and the right. You know, just all this other stuff sort of follows. Okay, so here's some actual Fourier transform theorems. So what is this saying? The Fourier transform is linear. What is this saying? If you delay something by nd samples, it's equivalent to multiplying by e to the minus j omega nd. What's going on here? Well, if you multiply by e to the minus j omega not n, you're actually shifting the Fourier transform in the frequency space. This is what happens in communication theory. It's called modulation. You're kind of shifting the frequency. Say I want to broadcast something from a tower at 1 gigahertz, but it's actually a picture, which we know is low frequency. You multiply it by a 1 gigahertz carrier signal like this. This is the multiplier. This is your signal. And then you send, that's now everything is shifted out. You have a low frequency signal that's centered around 1 gigahertz. You can send that out of an antenna as maybe an ATSC format signal, which is what broadcast television is now. Here it's HD TV, right? If you have an antenna, you can get like, you can still use an antenna to get TV, right? Let's see. And so, yeah, if you time reverse something, that will conjugate, we kind of already saw that, and that'll conjugate the Fourier transform. And multiplication by n is kind of like, it's surprising, like taking the derivative of the Fourier transform. If you, of course, this is something, so what do I put a multiple boxes around this? Multiplication in the sample domain is convolution, or multiplication in the Fourier domain is convolution in the sample domain. And the converse of that, this is convolution. Convolution, and this is actually very important for understanding chapter 4, which is our next subject after the midterm. Multiplication in the sample domain implies convolution in the frequency domain. Okay, there's a duality there. This says convolution in the sample domain is multiplication in the frequency domain. And the corollary to that is if we multiply in the sample domain, that's convolution in the frequency domain. That's what this says. And then there's Parseval's theorem, and actually Parseval's theorem is the kind of thing that is the crux. This is what people here in compression use this. They say this is the energy of a signal, right? Remember how I said that thing about energy compaction? The energy that you have in a signal in the sample domain is exactly equal to the energy that you have in that signal in the frequency domain. And since it's 2 pi periodic, if you're in the discrete domain, they only integrate over a 2 pi interval. And so what they're saying is that the energy doesn't change, but the location of that energy does change. If you have, say, one frequency, right, in a signal, it's going to exist for the entirety of that signal. If you take its Fourier transform where it actually occurs at 2 places, you only get an impulse at 2 different locations. So something that has values everywhere in the sample domain will occur only at 2 locations in the frequency domain. So, and that goes back to the Fourier transform of signals, right? So we talked about the Fourier transform, that's coming up next. Yeah, I don't know where that went. Where was our table of Fourier transforms? Yeah, here it is. Yeah, so if you have a cosine, you get a delta here and here. So this function exists for all time. So there is no index n where it's not equal to some non-zero value. Well, I guess, there'll be 0 crossings and stuff, but this will have non-zero values generally everywhere. This function over here only has 2 non-zero values due to these 2 delta functions. So a signal head of values everywhere is reduced to 2 values. That's compression, right? So it's compaction. So we're taking this signal that has all these different values that we'd have to keep track of, and now there are only 2 values I have to keep track of. That is the big power, the compression power of the Fourier transform, or in this case, the discrete Fourier transform. They both have the same power. This Fourier, but we use it in the discrete sense. Yeah.
So if you're in your Fourier or in your frequency domain, if you have an oscillatory function, does that mean that your actual signal is oscillating in frequency?
It means it's frequency content. So if it's magnitude spectrum, it presents as a oscillatory function. All right. So, and I think what does this bring to mind? Let's talk about the brick wall So the brick wall function, if we take the Fourier transform of this, does anyone remember what it looks like?
Oh, yeah, it'll be,
It's sort of, it's the sinc function, sine of x over x, sine of pi x over pi x, actually, right? It's a sinc function. So, and so what's surprising is that if you can have highly oscillatory functions in the Fourier domain that end up actually being finite and actually don't look like they oscillate at all. So it's really, you can have some surprising contradictions there. Right, and so this is the sinc function, sine pi x over pi x. And so if the Fourier transform of that is actually something that goes up, it's a brick wall kind of function. But if you think about it, the brick wall itself has all frequencies, like a step function. Has all frequencies because it's got an infinite derivative. So therefore, since it's changing so rapidly, we talked about that it's going to have infinite number of frequency components because it has to change so quickly in such a short period of time. Okay, so this is kind of all kind of mathematical insight, but we need mathematical analysis tools here. So mathematical analysis tools. Computing the DTFT of exponential signals. Okay, so here, say that we have an h of n and we want to find its DTFT. Well, we basically just need to plug into the equation. But I'm showing you a tricky little skill here. If you want this delay to actually be echoed in the exponent of 1/2. Why is that? So the reason that you want that is because you want to use one of the Fourier transform properties to do the Fourier transform. All right, the Fourier transform of this signal is actually easy to do using Fourier transform properties. This is 1/2 to the n, u of n, delayed, convolved with delayed by one sample, right? And we know the Fourier transform delay property right here. If we take a signal and delay it, it's multiplying by e to the minus j omega nd. So if we have this signal here, what is its Fourier transform? Well, the delay is 1, so you'd be multiplying by e to the minus j omega, and this would be the delay, right? That's a way to easily Fourier transform this function using properties. In order to do that, we need to factor out a 1/2 to get the 1/2 to the n to really be 1/2 times 1/2 to the n minus 1. Then we have this term, which we can easily transform as this, and then we have this 1/2 out in front, so that 1/2 comes in as a factor there, and this is the DTFT of that, where I did not do any calculation at all. I just knew the Fourier transform of the Fourier transform of alpha to the n u of n, and I knew the time delay property. Right? With those two properties, I didn't have to do a single calculation. Okay, so I'm pointing that out so when you see functions where the power of n is distinct from that inside, say, the step function, factor stuff out. Say that this was n plus 1. What would I do? So yeah, exactly. Let's factor out 1. What if this was n minus 2? Right, you want to basically factor out 1 over that, right? So you can move it in either direction, okay? By just factoring out the appropriate number. Make sense? Exactly. We want to match this to this, and then represent this as the Fourier transform of this function. So some constant times the Fourier transform of this function delayed. So we use the delay property that gives us this e to the minus j omega 1 because we've delayed the function by 1 sample. So according to this property, according to this, so mark this important. according to this property, the delay property, we're multiplying by e to the minus j omega 1, right? And so that's why this factor comes out here. Then this, right, this factor is just the Fourier transform of 1/2 to the n u of n, right? That's alpha to the n u of n. And so that's how we get this term. But we had to factor out this 1/2. So we also have to put that factor in again, which is why this is the final solution. All make sense? Okay. So again, Fourier, so convolution in the, this is the very, very important property. Convolution in the sample domain is multiplication in the Fourier domain. And we can do this and actually solve difference equations quickly this way. So if we have a difference equation that looks like this, we can take the Fourier transform of that difference equation. We're going to be repeatedly applying the delay property because we have a delay of +1 here, right? And we're just basically plugging in x e to the j omega for x of n, calling it, that's going to be whatever the DTFT is. And we plug in y e to the j omega for y of n. So term for term, we have x, this would be y e to the j omega is equal to x e to the j omega times e to the j omega 1, right? This is, this term right here is the same thing as writing down x of n plus 1, right? It's the same thing. I just put it in the Fourier domain, right? And this term right here, this is x of n in the time domain.
What if n is scaled in your input, like x of 2n plus
2n plus 1. Okay, so if you have, so that's going to be a stretch of the, you'll have to use a property for that, but essentially if you do, what does 2n do to frequencies? Think about, that's a compression, right? So in this case, if it were 2n plus 1, it would be a frequency doubling because you're squeezing the frequency by 2 and then a e to the j omega 1, right? So, and I don't know if that's here. Okay, so it's not here. I won't ask you that, but you can do it. It's not like you can't do it. You can.
1. Does it affect the real, like the coefficient?
I mean, people do it all the time. Like students had fun with my voice one year and frequency. Like if you want to do Simon and the Chipmunks, anyone know who Simon and the Chipmunks are? So you just take the any audio file, Simon and the Chipmunks. How do they generate this? This is ridiculous. So how did we get here? Simon and the Chipmunks. Anyways, do they have any audio? You can make anyone sound like a chipmunk. All you have to do is frequency double them once, or if they're real an alto, maybe, or baritone, or maybe twice. You just, every time that you do 2, you're basically jumping an octave up or an octave up. So you do the opposite. You do 1/2, right? And you should put, but this will make them go up. And they don't seem to have any audio. Is there any audio? Anyways, so I think I'm just not going to pursue this farther. It just makes your voice go up an octave. It's, yeah, so you can do that. Frequency doubling, frequency. By the way, that's what Hendrix does when he does the Octavia. So a lot of guitar soloists, they have a pedal. You step on the pedal, it doubles your frequency, and use it for soloing. So it's used all over all sorts of stuff. Let's see. So here we are talking about this. Well, okay, so we can factor an x out of this. So we do. We factor an x out. And if we factor an x out, we get e to the j omega 1 minus 1 times x e to the j omega is equal to y e to the j omega. And then if you multiply both sides by 1/x, you get y e to the j omega over x e to the j omega is equal to e to the j omega minus 1. And y over x is actually h, right? Because we have the convolution property that says y e to the j omega is equal to x e to the j omega times h e to the j omega. that's saying that the convolution of X and H is equal to the output Y, right? So therefore, Y over X has to be H, right? And we can calculate from this difference equation, we can directly calculate the Y over X. So that means that we also have H. So that means that the impulse response of this difference equation we just got. So if you don't feel like solving a difference, if you're trying to solve a difference equation and you want to get its homogeneous response, you can just take you can use the Fourier transform to get it if you want. Right? You can just use this is a way of getting the homogeneous solution of a difference equation. Of course, you have to inverse transform. What's the inverse transform of this?
It'll be 1 over 1
Well, what's the inverse transform of 1? Delta function. This is a delta, so this is 1 delayed by 1. This is this is e to the j omega. So think of this as some function multiplied by e to the j omega 1. I'm going to say this is the number 1 multiplied by e to the j omega. So think of it as a delayed, or an advanced rather, delta function. So this is delta of n plus 1, the inverse transform of that, right?
What the whole, wouldn't it be
Well,
delta
okay.
n plus 1 minus delta?
Yeah. And then we do the inverse transform of the second term. So we just did the inverse transform of the first term. And of course, that is exactly what we have to derive, because if this is a finite impulse response system, we can also get the impulse response by just substituting x delta for x, which is what we did in a previous lecture. Like the lecture when we talked about sample domain representations of linear time invariant systems. We said we can just plug in delta for x and we get exactly this anyways. And we're verifying that, yes, this is the Microsoft Excel of mathematics. You can solve the same problem in lots of different ways, right? The Microsoft Excel is my de facto example of, like, there's so many different ways to do one thing that it's hard to do it right. There's no exception. This course is no exception. You could choose your path and then know that path, right? That's the only way I survive Microsoft Excel. This is how I suggest you survive this course. Okay, so here's a difference equation. We're going to calculate its impulse response. It's the Fourier transform of its impulse response. So what do? We just substitute y's for y of n. Wherever we see a delay, we multiply by the appropriate e to the minus j omega. So we have 3 y e to the j omega, that's the first term, minus 2 y e to the j omega times e to the minus j omega, 4 x e to the, where's 4? Oh, here it is. So we simplified it a little bit, but we have 4x e to the j omega. And where's our 3? Well, what are we doing here? This would be, oh wait, so x e to the j omega times 3. So that's there, right? So we have this is equal to this. What's in the middle here? Well, I'm just kind of substituting in an h e to the j omega, saying that you could consider this 2 convolutions. It's kind of belaboring the point. But in the final analysis, you factor out your x's, you factor out your y's. So if you factor out your y's from this side, y e to the j omega gets multiplied by 3 minus 2 e to the minus j omega. And on the left side, you have 4 plus e to the minus j 3 omega multiplied by x e to the j omega. And you divide the y by the x's, and so this goes underneath this, and you get the solution here. Very quick, very easy. The key principles you have to remember are the delay property and how to do algebra, right? It's the delay property, it's like almost nothing else, right? So delay property is, that's why I label it as really important. So this is a DFT of a difference equation. Well, we kind of done this a lot. I don't know if we're doing anything important and new here. This is the same exact thing that I just did on the previous slide. So I'm just going to go on to the next slide. All right. All right. So DTFT and IDTFT to compute h of n. So if you wanted to get back from an h e to the j omega to an h of n, we have to go through the inverse discrete time Fourier transform. If that is an IIR difference equation, remember, IIR difference equations always lead to denominator functions. Why? Because you end up with this term, like some kind of equation here. It's going to end up going into the denominator when you divide through to the other side. This is IIR because there is feedback, right? Y of n is a function of other y's. So whenever you have a non-zero order difference equation in y, right, where y is a function of other y's, you're going to end up with some kind of polynomial or function in the denominator, non-trivial function. It's not going to be the number 1 or something. And so in such cases, when you apply the IDTFT, you're going to have to do some, what do you do in such cases? Well, in general, you will always be able to do the partial fraction expansion. If the numerator is simple, like this, you have a bunch of numbers divided by the same, like if you have 3 plus 10 over 17, how do you write that as 2 fractions? Yeah, so why are you asking me these trivial questions, Dr. Willis? This is like, this is the senior year of my engineering career, and you're telling me this kind of ridiculous stuff? Why am I telling you that? People look at this and get confused that this problem that you're looking at is different. Is this different? No. These are just numbers in the top here. This is a number and this is a number. So I can just split this apart, right? And I can say 1 over that fraction minus the other thing over that same denominator. And just, you're done. I can directly inverse transform this. Right? So I hate to kind of patronize you with these stupid questions, but I want to point out to you that, don't make the problem harder than it is. Don't make it harder than it is. When you have these partial fraction problems, there's just fractions, and there's a variable floating around, so you have to do some bookkeeping. I apologize for that, but I kind of want to keep us thinking that maybe this isn't as hard as we want it to be. Maybe it's easier if we kind of say, hey, hold on, what's going on here? How can I simplify this? Can I make my life easier? Because you could go through a whole partial fractions, experience to try and tease this apart and come up with, well, how are you going to come up with this one? You have to come up with these constants and so forth, where it could just be a much easier exercise. Okay, so if you inverse transform this, well, what's the inverse transform of this here? 1 over 1 minus 1/2 e to the minus j omega. So that's alpha to the n u of n, right? And the alpha is 1/2, so it's this term right here. All right, what is the inverse transform of minus 1/4 e to the minus j omega? What does this mean, e to the minus j omega? You have a delay or a shift of 1, or like it's a -1 that's going to happen. And then we have a 1/4, that's linearity. That's just a constant you put out in front. So this is again, a delayed alpha to the n u of n. So it's 1/4, what's the thing? So 1/4 times 1/2 to the n minus 1, u of n minus 1, because it's delayed. So this is the delay property. This is the alpha to the n, u of n gives you this 1/2 in the u, right? And then this is that constant 1/4 that's out in front. So everything there has a purpose for being there, and we'll utilize sort of a different attribute of all these properties. Does that all make sense?
So the constant, because the constant doesn't affect the delay, right?
Yeah, remember the constant, it's linearity. I can take the Fourier transform of some really complicated thing and then multiply it by 5. And I have 5 times the Fourier transform of that really complicated thing. So this is just the number 1/4 out in front. And it's a example of the scaling property. So the Fourier transform obeys the scaling property. It is a linear transformation, and yeah.
So, this makes a lot of sense, but I'm a little confused when I think about in my Signals 2 class, when we do this continuous inverse Laplace or inverse Fourier, an exponential shift of, let's say, negative AT would be a shift of positive A in the Fourier domain. I have it pulled up here. But in here, it seems like we have a shift to the left, and also you also have a negative shift in the continuous method.
No, that's so it's consistent. So if it's so this is ND is positive, and then you have a minus ND here.
Right.
And
So-
that makes sense, right?
they shouldn't be different. Yeah, we should, probably not the best place to try and tease it out right now, but if there's an inconsistency, there shouldn't be.
That's not good.
Yeah, that's not good. Like, but this, I can tell you, this isn't wrong. We'll have to see what's going on there, and then we'll update all the folks that I'm sure you're all very concerned, but just you'll have to wait until next class and sort of just believe that the world will not break between now and then. We can update you as to what exactly is going on there. You know, there might be a reason for it, but at the moment it kind of escapes me. But anyways, that's an exciting to be continued discussion. Let's see. So we understand this. So we'll move on to the next one. So now this is, so by the way, this is an IIR difference equation. So this is, if you have an IIR difference equation, this is a technique for solution slide. There's a lot of different techniques for solution slides, but I try and give you a lot of different tools by which to combat the problems that you'll see. And this is how you approach it. So if you're faced with an FIR difference equation, so I actually would not even, if there's a really strong reason to take the Fourier transform, go ahead and do it. But again, if you have a FIR difference equation, you can just plug in delta for X and be done, right? And so this is just an example of how to take it back. So remember, if you see anything that looks like just an e to the minus j omega, that's a delta function, a delayed delta function. And so you're taking the inverse Fourier transform, and we did this by hand a little bit ago, but it's sort of written out in slide format here. So FIR filters will always just be like, if there was an A in front of here and a B in front of there, well, then you just have an A in front of here and a B in front of there, right? It's by linearity, you know, and even if that constant were complex, like maybe B is in fact, I don't know, 3.2 e to the j 10. You just take it down. You don't let it distract you. Okay, it would actually, well, if it's if it's a general e to the minus j omega, then that would be a delay. But if it's just a constant, it doesn't get combined. Okay. All right, so here's the eigenfunction property revision 2. Okay, and so again, we're talking about eigenfunctions, and we put an eigenfunction in. So if x of n is an eigenfunction, what is an eigenfunction? A complex exponential is an eigenfunction, or any linear combination of complex exponentials is also an eigenfunction. Then what comes out? Well, the function comes out multiplied by a complex constant. That complex constant, we talked about at the beginning of the lecture, sort of here in the lecture notes again, is just the Fourier transform evaluated at the frequency of the input. So I don't know, what if I say I have a system 1/2 to the n u of n, and I put x of n is e to the j 5n is x of n. I ask you for the output. This is an eigenfunction problem. I give you an h of n, I give you an x of n. The x of n is actually a complex exponential or a sinusoid. And I ask you for what the output is. What is y of n? How do we calculate it? First thing we have to do is we need to get this character here. We don't have h e to the j omega. We need it. How do we get it? What is h e to the j omega? Right, this is Fourier transform of h of n, which is this. What is the Fourier transform of 1/2 to the n u of n?
1/-.
That's h e to the j omega. Okay, and now we have that. Now we have to evaluate it at what value?
5.
Okay, so how do we evaluate this at 5? We just plug in 5 for omega. Okay, now we look at this and we say, okay, what does that mean? This is a complex number. This is exactly what I would like you to think. This is a complex number. And so what comes out is this. So y of n, I could just simply write this. Y of n is equal to 1 over 1 minus 1/2 e to the minus j5 times e to the j omega g5 j5n. That's technically right. Now, if I wanted to simplify things, which say I were to ask you for the phase of the output, then I have to do more work. Or say I wanted you to find the magnitude of the output. Like what is then I'd have to take this complex number and convert it into magnitude and phase. And then the magnitude would multiply the magnitude of R, which is 1 here. And the phase would add with the phase, right? Yeah.
So I'm a little confused when you just wrote y of n. So I thought when you write y of n, you need to have, it's a convolution and not a multiplication in that.
But this is for eigenfunctions. This is so the eigenfunction property is a special case where we actually know what the output will be. And something that we kind of had at the last slide of lecture 6, and again, we're revisiting here. And we know that in this particular case, and I don't want to pull up the slide because we're sort of short on time. But we know that we already know what the output is, and it's just the same thing as the input multiplied by a complex constant. And that was what the last slide of lecture 6 gave that conclusion. And we're sort of so it's a special circumstance, I guess is what. So in general, what you're saying is absolutely true. Like you have to do the convolution, but in this case, the convolution is in fact coincides with this result.
And that is because the input is a sinusoid, right?
That's because the input is a eigenfunction,
Right.
which and an eigenfunction, a sinusoid is an eigenfunction.
Right.
So I want to say if the input is an eigenfunction because it includes both sinusoids and complex exponentials,
Right.
right? Because this input here is not in fact a sinusoid. This is a complex exponential.
Right. Because you can have like an envelope and an input, which would be like a.
That's
complex
well,
and a
if
sinusoid
it's so an envelope like e to the minus n e to the j omega naught n, that's kind of not exactly the same thing because this is not an eigenfunction. This is an envelope. So and it's not a linear combination, it's a multiplicative combination. So it doesn't work for that one. Yeah. So this if this constant if this were not a function of n and a constant, it would work.
Right.
But because it's a function of n, it's the scaling property is it's sort of its own, it's a separate function. It's the product, and this is actually ends up being the modulation property. You're multiplying two functions. So in the Fourier domain, this would be the convolution of the Fourier transform of this with the Fourier transform of that. This is a delta function. So it's basically the Fourier transform of this is located centered around at that frequency. It's what happens. But
Well, you wouldn't give us something like that.
no, I won't give you something like that. Certainly, it's not an eigenfunction problem, so I certainly wouldn't give it as an eigenfunction problem.
All right.
Okay, sinusoids are eigenfunctions. And so, yes, when you do put them in, you get a theta as the change in phase. So this is basically saying, what do I do? Well, I write down a trigonometry, a function, cosine, whatever, cosine or sine, and I just show you that this is actually a combination of eigenfunctions. Here's the eigenfunction that we know and love, and here's its complex conjugate. So the only difference between a sign is that you would have a minus sign here instead of a plus. If this were sine of cosine omega, and this would be a minus here, and everything else would be exactly the same.
To the j in the denominator.
Or yeah, there would be a j out in front of all this, kind of multiplying everything. So I don't want to kind of look up everything, but that's the only key differences. And so those are also eigenfunctions. And when you put them into linear systems, then what comes out is the magnitude response evaluated at that frequency, which multiplies the sinusoid. So here we had A was the magnitude going in. So you have A times the magnitude response evaluated at omega naught. What does that mean? You need to take the magnitude of this number, right? And that's what would go. That's what would go here. And then you get the phase of that number. And the phase is what goes here. All right, just as a matter of review, because I know, and it's just because I like to torment you and make you angry at me for asking stupid questions. How do I get the magnitude and phase of this number?
Multiplied by conjugate.
So yeah, you can multiply by its conjugate and get the magnitude of the numerator we know is 1. Magnitude of the denominator is that times its conjugate, right? So it's 1 minus 1/2 times 2 cosine 5, right? Okay, you guys done that enough, right? So it's 1/2 times 2 cosine 5. I love to see that we've been practicing. And then the last term is minus 1/2 times minus 1/2, which is 1 plus 1/4, right? Right, plus 1/4. And so we've just calculated the magnitude of that complex number, right? That's its magnitude. Can you punch this into a calculator? You bet. That's what you would substitute in if the cosine, if this frequency went into that system, 1/2 to the n u of n, this would be, you'd multiply by this, that would be your multiple there, right? And so how do we get the phase of this? What's the phase in the numerator? Yeah, 0. So it's 0 minus, what's the phase of the denominator? So let's write it out in a rectangular format. E to the minus j5. Okay, so what's the real part? 1 minus 1/2. 1 minus 1/2 cosine 5, right? That's the real part, and that's in the denominator. What's the imaginary part? Minus sine 5, tan inverse. Done. Do we have the phase of that number? Yes. So you can just write down the solution if you use the methods I'm telling you to use. You can just write down, you have to then punch this into a calculator. But you've basically written down what you need to punch in. Do that before you punch it in, because it's always, or you can type this directly into MATLAB, right? And it'll just be right. Okay.
Are we missing a 1/2 in the numerator though?
I don't think so. Yeah, we are. In fact, we are. Thank you.
Oh, yeah.
Yeah, it would be positive. Thank you for these arithmetic fix-ups. Yeah.
So then we look over the notes and I'm gonna be super confused.
No, yeah, these are all good things. Thank you for the suggestion, for fixing that up. But we're all good there, right? It's just, you basically can just write down the solution. Any other questions about that? Like that's procedure on that. That's technique for solution. Okay. So this is an example of a system, right? And we put this as input, and then we want to figure out what comes out, right? That's an eigenfunction property. So this shows you how to calculate the magnitude response at, so what is the frequency of this input? This is the input, x of n. What is the frequency? It's this thing in front of the n, right? So when you're trying to do these problems, you always have to remind yourself, what is the frequency of the input? And what is the phase? The frequency is anything that is multiplied by n is a frequency. Because frequency has what units? Radians per sample. So therefore, anything that has samples multiplied by it, that's going to be frequency. So if there are multiple terms in n, you have to collect all those terms. That is the frequency, right? Anything multiplied by n. You collect all that stuff together, and whatever you have inside that bin, that is your frequency. So if I had something like cosine of, I don't know, 3n plus 5n squared plus 2, I would never do something like this to you. But what do you do if you're faced with such things? You factor an n out. You gather anything that's multiplied by an n. 3 plus 5n is all multiplied by n, right? So this is something that changes frequency with the sample index. So in this case, this is called a linear frequency, linear FM chart. So you basically frequency modulating. The frequency is changing as a function of the sample index. Every time you go to a new sample, you're at a different frequency. Wacky, wild stuff. But it's, if you just take this perspective of anything that it multiplies by n is the frequency, then it just becomes less complicated, right? It's just not, I will not do that to you on either. I don't know if I ever do this in any homework, but I won't do it to you in a test or quiz situation. This is not the fundamentals of signal processing. This is a little bit more advanced. This is kind of stuff they do in radar, by the way. So when they're doing, it's radar to figure out this, how the weather is going, or whether radar to detect planes, or radar to form synthetic aperture radar images, all of that stuff uses linear frequency modulated chirps. Very cool stuff. Okay. Okay, so what do we have here? Yeah, so we don't have this. We have none of this. But we do have a general conceptual way of finding the frequency of anything that we're given. If it's a trigonometric function, you look inside the argument, see anything multiplied by an n, gather it together. Whatever is in that bag that multiplies n is your frequency, right? And so when we do look at that, well, the only thing that multiplies the n here is 2, and that is the frequency. So hence, when we proceed to solve this eigenfunction problem, we need to find the magnitude response at omega equals 2, and the phase response at omega equals 2. And this is just going through the algebraic procedure of calculating those values for this particular function. This is the function. And, if we want to calculate the magnitude of this, we multiply the numerator by its complex conjugate. You get this and evaluate it at 2. We get this. And, denominator, we get this. So no surprises there. And in the final analysis, we come up with a little bit of strangeness. This is an E to all of this stuff. So a little bit of strangeness in the way that the equations are rendered here. But you can actually produce a prediction of the output, and it looks kind of complicated, right? So this is it. We came up, this was a constant that's multiplying, so we just write it out in front. And then this is the phase actually ends up being 2 terms, these 2 terms. So we don't care about that. We just write that out as data. We put that in the end. And yeah, there's a bunch of math there, but like I can punch this into MATLAB and it'll come up with a number. And that number will be correct. And in fact, if we actually do this by convolution, that's another way to, I think I do that with, here it is. I do that with a MATLAB problem to actually show you that, in fact, the eigenfunction property is no joke. It's literally true. So I take some system and I input an eigenfunction and you calculate the analytic solution, and you find that the solution that you get from doing all the convolution is in fact equivalent to the solution that you get using the eigenfunction properties. It kind of sort of double checks that what we're doing here is a valid exercise. So this actually MATLAB example doesn't do what I thought it was going to do. This just solves a difference equation. And so here we have a difference equation, second order in the input, first order in the output. By the way, is this an IIR impulse response or FIR? IIR, because there is feedback. This term makes it IIR. The output at n is a function of previous outputs. Whenever that's the case, you'll have an IIR filter. If I were to delete this term in Y, it would be FIR. And so what's going on here? Well, we have an input signal, and this input signal is in fact, if we look at it very carefully, we find that it is. The input signal is 2 pi 1 over 10 to the n. And so that's the input to this system. So is this, could this be phrased as an eigenfunction problem? If this system had 0 initial conditions, then this can be phrased as an eigenfunction problem. Why did I have to say that? Because it's only linear in time invariant if it has 0 initial conditions. And we can only apply the eigenfunction problem for LTI systems. So yeah, so that's the case. Yes, it's all satisfied, and we can get the output. So there's a MATLAB example to go along with this. I would love to be able to pull that up if I don't know if I have the time to do so. But it is under the MLX file for lecture 7. That'll show you the actual verification in MATLAB of the eigenfunction property. All right, well, it looks like MATLAB is not going to be responsive enough to get us all started on this in time, but here it is. Anyways, if you wish, you can certainly download the MLX file and run the MATLAB, and it basically validates this eigenfunction property that we previously discussed. Okay, so we have one more lecture before the midterm exams. So I just want to reiterate that for the midterm exam, be prepared to come to class, take the exam in class, the requirements. So I'm going to have all the students be facing the back wall so that I can see everyone's screens and be sure that everyone is using the materials in the way intended for class. Just be aware of that. I'll also be bringing in some power plugs so that everyone that needs to plug in can do so. If you have maybe your laptop battery isn't like totally ready for that. And so those are some materials that will be available to you. Make sure you have ability to capture your work as you go. Our lecture on Thursday will be a sort of a recap. But this is the last slide on this lecture. So the next lecture will be lecture 8. It'll be a recap of all linear time invariant theory and also serve as sort of your preparatory for the midterm. You have a question? Yeah, you'll be having the quiz that follows up on the homework. So you'll have that on Thursday. Any other questions?
Yeah, you're gonna give us like a.
We're gonna have there'll be a homework assignment that's sort of a prep for midterm kind of thing that'll be distributed as well. So that'll be assigned as of today.
Okay.
Yeah, and just allow you to both practice submission. I'll have that question to copy and submit, and it'll have a number of questions. It is not, by the way, 100 on that does not imply 100 on the midterm. It does not imply the questions are the same as the midterm. It doesn't imply anything. It's just practice. Yeah. Remember, you have access to all of the slides. So the slides actually have all the Fourier transform tables in them. It's a matter of whether you want to look them up or not, so if you want to not have to look for them in the slides, you might want to measure. I would memorize the delta, the basic ones, delta, step, alpha to the end.
Do we need to download the notes and stuff, or can we go to the campus page?
Yeah, you can go to the Canvas page and actually use the notes. Yeah, absolutely. I expect you to just use the notes right off the Canvas. Yeah, but I don't expect you to open your quiz assignments or any of your other things. Just use the notes. That's why people are going to be, having the. No, you can only use. So I want to be very. You can't bring anything into the room or use things apart from the what I specify, which are the slides and the MATLAB. No, listen, there's just too much chaos. You're gonna have your laptop up there, right? You're gonna be doing it all on Canvas. That's actually gonna slow you down. Yeah.
So you're not gonna give us like a topic list of what to study for the exam, where it'll be like just make sure to know all the sections of the chapter.
Yeah, I think the content of the exam is pretty explicit in terms of what's listed for readings on all the assignments and what's in sections from the textbook, homework. I
the
mean,
whole 9 yards.
I don't know. Yeah, it's everything. Yeah.
I couldn't have a question for that.
Let me stop the recording real quick. Okay. So
We use the homework solution.
no.